Okay, so thanks a lot for the invitation and thanks for being here. So I will give you some information on the topic of the carbon footprint of our research field. And to start, it's always good to put things in a context. And I think a very good illustration of the context is given by the planetary boundaries framework. I don't know how many of you are aware of this framework or know what it's about. So the basic idea is that the environmental scientists were asking the question whether human activities actually destabilize the Earth system. You know, I mean, we are currently living in what is called the Holocene period, over 10,000 years of stable climate conditions. And the question was, I mean, are our activities destabilizing this stable period? And the answer they found is yes. And in fact, they identified 9 planetary boundaries, 9 is essential areas that are important to maintain the Earth system. And what they found out, and this is illustrated here in this graph, is that 6 out of these, we are no longer in the safe operating zone for 6 out of 9 of these planetary boundaries. And the areas where we are no longer in the safe zone are, of course, climate change. You know all about this. But there are even, I would say, more worrisome issues like the biosphere integrity. This is the biodiversity. Maybe you heard about the 6th mass extinction. You have the land system change. This is deforestation. You have freshwater change. You have biogeochemical flows. This is basically nutrients flowing in the water, in the ocean, posing problems. And what they also call here novel entities. These are all entities that do not naturally exist in the environment, like plastics or genetically modified species and so on. So in fact, we have climate change, but we have in fact a large variety of issues. And so we should be concerned about that. And the question why scientists, I mean, why we should be concerned about this is I think very nicely summarized in this report. Unfortunately, it's only in French. It's a report from the CNRS Ethics Committee. The president of CNRS asked basically the Ethics Committee, so what's the role of the scientists concerning all these environmental issues? And what they said is that it's an ethical responsibility to integrate these issues in our research activities. So first, I mean, these are citations that are translated from this report. First, they said there's a broad agreement emerging on the need for research, like any activity, any human activity, to contribute to the effort to reduce greenhouse gas emissions. The second point, I think that's very important to say that taking the environment into account is an integral part of research ethics. Normally, when you think about research or hear about research ethics, it's about animal experiments or experiments with embryos and stuff like that. Environment is the same thing. I mean, we have to consider it at the same level. That's what they're saying. And then they say it's the responsibility of the scientists to think about their activity with regard to environmental issues. And finally, I mean, they say this does not only concern the impact of our research practices, but more generally the negative or positive impacts that comes from the choice of the research subject and the path to treat it. And this in the short, medium, and long term. So I think these are very important statements. And at least for my presentation here, this is basically the context and the frame of that. Now, taking up these considerations, I mean, in astronomy, there is now quite, I mean, just demonstrating why we have the session this morning, there's quite some activities, quite some reflection about the carbon footprint. And here I summarized 5 basically works that exist in the literature about assessing carbon footprints, specifically, for example, for communities like in the Netherlands or in Australia, or for individual labs like in Germany, US, and IRAP, France. This is our lab. And the first thing that you recognize, I mean, here you see the carbon footprint per employee in these communities or in these labs. And by the color code, you see different sources of impact of greenhouse gases. Office means basically the building, heating, electricity, and so on. Employer means everything that relates to the employees, commuting, lunch, and so on. Travels is, of course, business traveling, and then you have computing. Purchase, so building, buying things and services, goods and services. And in brown, the use of observatory data. So what you see is there are quite important differences among the assessments. One reason for these differences is the carbon intensity. That's, for example, true in Australia. They use coal for generating electricity, and this explains why computing, for example, the red bar, is so important. But another reason why there are so huge differences is that not everyone used standard methodology to make the assessments. And the second, even more important aspect is that some of these studies just excluded important emission sources like purchase and use of observatories. And what we did at IRAP here in Toulouse, we tried to be as comprehensive as possible. And that you see here in this in the fourth bar, where you see that all of a sudden the use of observatories shows up tremendously. And observatories here are ground-based observatories or space observatories. So what we estimated that the contribution per astronomer, so this is a tiny difference here in the graph you see per employee, including technicians, administration. But when you just put it on the astronomers, then on average, on every astronomer, you have 36.6 tons of CO2 equivalent every year related to the use of observatories. So we wanted to understand this more. And what you do is, in fact, if you really want to understand comprehensively all environmental impacts, so not only focusing on carbon, but including everything, then what you do is you do a life cycle analysis. And just for those who don't know this method, just an illustration, basically, this comes from the European Space Agency. They are doing this since a decade or so. So basically, you look at an activity, and in this case, is, for example, rocket production and launch, and you consider all impacts that come in the life cycle of this product. Basically, looking at what flows into the process, what minerals do you use, what energy is consumed, and so on. And then looking what comes out of this, like greenhouse gases, eventually does it deplete the ozone layer, air pollution, water pollution, and so on. So it's really a comprehensive analysis of environmental impacts of an activity. And I show you now two examples, and this is work that we did at our lab. So this is an example of a ground-based telescope. Specifically, that's a telescope that will be erected in La Palma on the Canary Island, will operate there for 30 years, and will observe, in fact, the sky to do gamma ray astronomy. And what you see here now, every bar is a specific environmental impact. So the first one is global warming. These are greenhouse gases. Then you have photochemical oxidants. This is the smog that you have in the cities, for example. Ozone depletion, so depletion of the ozone layer, air acidification, let's see, the acid rain, particulate matter, so these are aerosols, and then you have toxicity on human, on fresh water, resource depletion, how much resources we take out of the environment, the use of land, the consumption of water, eutrophication, so the nutrients that flow in the terrestrial system, freshwater system, marine system, and last, ionizing radiation, radioactive decays. And the different colors show you different contributions. So blue is the construction of the telescope structure. Green is the construction of the camera that sits on the telescope. Orange, that you cannot see in these bars, this is transporting the telescopes to the site and so on. Then you have assembly, integration, and testing in purple. And then red is power consumption of the telescope once on site, and gray and brown is maintenance operations. And what you see very clearly here for a ground-based telescope that operates for 30 years, the power consumption during operation is a very important contributor. And specifically here in La Palma, they have a very dirty energy production. It's diesel generators. It's around 1 kilogram of CO2 equivalent per kilowatt hour that is emitted. And that's why this is showing up so importantly. So indeed here, I mean, greenhouse gases are a major point of concern. But you see the second most important point of concern is resource depletion. When fossil fuel is evident, if you use diesel to generate electricity, you have an important fossil fuel resource depletion, but also mineral resource depletion. And this relates essentially to building the structure and specifically the camera. Now, these are all the electronics that go in the camera. That's why this green bar is so huge. And this is all this shown here is in a specific unit, which is called points, which is a kind of normalization to aggregate environmental impacts. And the final sum is when you just sum up all these bar, you get a score of 351. And this means that the environmental impact of the system is equivalent to the environmental load of 351 average persons on this planet per year. Now we did the same for a space instrument, and here this is not the entire life cycle of the space instrument. This is just producing a space instrument. That's maybe what eventually happens in your labs when you build a contribution to a space mission. So this is not including the satellite, and this is not including the launch, and this is not including the operations. And here you have the same indicators, and the different colors are XM. These are all pre-flight models. Then FM is the flight model that is produced. Orange transport, purple again assembly integration test, and green, light green office work, and gray traveling. So you see here the structure is quite different, yet the outcome at the end is the same. The biggest bars are on global warming and on resource depletion. And very interesting, what comes in here, when you build a space instrument, I mean, the mass of the space instrument is very small. It's a few hundred kilograms, maybe a ton if it's really a big thing. But the mass, the weight of the stuff you're building is in fact extremely small compared to when you do, for example, a ground-based telescope. So what weighs in here mostly is just the office work. Just people sitting in offices needing electricity, heating, air conditioning, consuming water, and so on. And this is the green light thing. And all the traveling you do when you build a space projects, all the meetings, and so on. So in fact, it's just the daily business basically related to the space project, which is an important contributor. And then another big point of concern is the assembly, integration, testing. Behind this are all the clean rooms. The clean rooms are very energy consuming. Maintaining stable environmental conditions consumes a lot of energy. And this shows up in all these studies that this is a very important contribution. So you see again, and interesting when you sum now up this, and this is just one instrument on a satellite, you see the single score is now over 4,000. So if you do space stuff, it's in fact extremely impacting, and I will come to this back later. Now, the real question is, okay, now we have all this information, what can we do about that? So one idea around is, of course, what is called eco-design, is basically trying to do the same thing, but just in a green way. And this is here an example of an ESA mission, Proba 5, where there was just a study with a long list, as you see it here on the left, of things that could be in principle improved, assuming there are no financial constraints, just assuming stuff that you could do differently, but without considering finances here. And that what you see here is, on the right-hand side, is the improvements that can be made. So, for example, global warming can be reduced to 45% or something like that. So you can gain, for example, a factor of 2 in terms of reduction of greenhouse gas emissions in this specific example. But what you also see then on the different indicators is you never win on all indicators. There are always winners and losers. So it's a trade-off. And of course, considering what are the important impacts, eventually it gives you different solutions. And the other message that you can take away from that is that when you just look at the average, well, improvements are around 20–30%. That can be made by eco-design, but there are no miracles. There's no 100% winner where you just can make a zero impact thing. It always will have an impact. You can try to reduce the impact, but I mean the margin is not so enormous. What can you do on ground? So as I've shown you, I mean, power consumption is a big issue. So people are looking, of course, into renewable energies. And this is here a picture of two solar panel sites in Chile, near the Paranal, where there are the big optical telescopes. And this was opened, in fact, recently. And that's certainly a good move. And just to illustrate what's going on here, this is data taken from ESO. This shows you here the annual carbon footprint as it evolves over time on the ESO sites in Chile. So in 2016, Paranal was powered just still by liquid petrol gas, very polluting. And then in 2018, they connected Paranal to the Chilean grid, electricity grid. And this almost gave a drop of a factor of 2 in carbon footprint. So very good. Then you go on in time. 2020 was COVID, so they operated less the telescopes. So that's why there is a dip. 2021, it went up again. And then in 2022, they connected Paranal to these big solar farms that you have seen on the picture, making again a drop in the emissions. So between 2016 and 22, they had even a reduction of a factor of 2 in their annual carbon footprint. But now the thing that happens is that they build a new telescope there, just not replacing the old one, just adding one more telescope to their sites. And it's in fact the biggest telescope in the world. It's just the size of this is like the Colosseum in Rome. And then they predict basically what they will have in terms of energy consumption from this telescope over the next years and the associated carbon footprint. And as you see at the end of the decade, the carbon footprint of their telescopes will just be bigger than it was in 2016, despite all these efforts to reduce the footprint over there. So you see, I mean, very clearly that the reductions are always annihilated by additional carbon footprint of new research infrastructures. You can say, well, this is just one example. So I looked into the entire history of our field of astronomy. And what you see here on the left is basically the number of operating facilities in a given year over time. And what is shown in blue or purple, these are space facilities. So divided by astrophysical, planetary, plasma sciences, solar sciences. And then on the ground, you see radio arrays, so arrays of different radio telescopes, single radio telescopes, and then you have optical infrared reflectors, OIR, and they are separated by ones that are bigger than 3 meters and ones that are smaller than 3 meters. And you see, I mean, we are completely dominated by ground-based facilities in terms of number. But when you convert this into a carbon footprint, it's completely inversed. We are completely dominated by space facilities. And okay, I have to go faster. What you see here, the scale is broken. So I mean, there's an initial peak related to the first space race, but we are again in this growing dynamics. So coming to the conclusion here, so the lessons that we have learned from these studies is that first, eco-design may lead to impact reductions, typically of the order 20–30%. And it's difficult to win on all categories. Reducing power use and using renewable energies are an important lever arm, and even for satellites, because you have ground support, you have data centers and so on. So also here, energy use is important. But, and this is really the very important lesson coming out from this, the impact reductions cannot compensate for the growing number and dimension, the size of new infrastructures. So there is no evidence for green growth. not in our field, and of course also not generally in the economy. And it's imperative to slow down to fit into the planetary boundaries. One way to do that, and probably we'll discuss about this and afterwards, it's to go out of competition and really to enter collaboration. Because at the end, I mean, just nature will dictate this. We have to fit into the safe operating space for humanity. Otherwise, we will have a very difficult time in the future. Okay, thanks a lot.